Welcome to week 10 of the ma161 calculus. My name is Götz Pfeiffer, and this video is about maximum and minimum values of a function, which collectively are also known as extreme values. One of the most important applications of the calculus is solving optimization problems. That's problems that seek to minimize the cost of doing something or maximize an area. Typical optimization problems in the real world are questions like what's the fastest way to get from here to there, or what's the cheapest way to get from A to B, what type of packaging can enclose the largest volume, or here's some practical question: at what speed does this car use the least amount of petrol? There's loads of optimization problems that arise in real-world contexts. This week we're going to set up the terminology that is needed to attack such problems with a view to sketching the graph of a function. So our point of view is that we're dealing with a function, and the typical optimization problem then is for which number x does f of x yield the largest possible value. So if an optimization problem can be modeled through a calculus function f, then the graph, plotting the graph, may help to answer such questions, may exhibit the regions of interesting or extremal behavior. And it turns out that the derivatives of the function, which is used to model the problem, can help to identify those points where f of x is optimal, maximal, or minimal, or extreme. So let's start by making this notion of maximum and minimum precise. There are some subtleties, as we will see. Starting point would be this definition. If C is a point in the domain capital D of some function f, then f of C, the value of the function at C, is the absolute minimum, is the absolute maximum value of f on the domain D, if this value f of c is greater or equal than any value f of x, where x is chosen as any point in the domain D. Similarly, f of c is the absolute minimum value of f over the domain D, if f of c is less than or equal any f of x, where x lies in the domain of D. Here in the diagram we see the graphs of two functions, and the orange dots here indicate on the left a typical absolute maximum value, for c equals 0 it seems. This graph indicates that all other values of the function lie below the value that f takes at 0. And here on the right we see a mirror image of this, almost a mirror image of this graph. The orange dot here, the value that this function takes at -2 is smaller, is less than or equal than every other value that we see here in the graph of that function. Collectively, I said this before, the absolute minimum and maximum values of f of x are called the extreme values of f, and here is an example which illustrates the occurrence of both types. This is essentially the sum of the two functions whose graphs we saw on the previous slide. Now this function f of x defined as 1 over x squared plus 1 minus 1 over x plus 2 squared plus 1 has a graph which looks like this. There's two orange dots. One indicates the absolute minimum value and one indicates the absolute maximum value of this function f. The maximum value seems to lie above 0 on the x-axis. The minimum value seems to be the value at -2, but that's just a rough estimate. With calculus, and we'll see how you do this, one can show that these extreme values actually lie at the points -1 plus or minus the fourth root of 4 over 3, where this fourth root of 4 over 3 is approximately 1.07. So this is a bit to the right of 0, the maximum, and the minimum occurs a bit to the left of -2. And then when these points on the x-axis are known where the extreme values occur, then one can calculate them by simply substituting these values -1 plus minus fourth root of 4 over 3 for x in the formula that defines f. And then one sees they are approximately plus or minus 0.8. That's an example of extreme values, the absolute minimum and the absolute maximum of this function. Sometimes instead of absolute maximum, one talks about a global maximum. The reason for that is to distinguish it from a local maximum, which is a slightly different situation. It may be the case that the value f of c at a point c is large in comparison, is larger than any function value nearby. When you choose x close to c and evaluate f of x, and f of c is still larger. That doesn't make f of c necessarily a global maximum, but it makes f of c carry some maximality, some extreme aspect. So here's a definition of a local maximum. We say that the number f of c, the value of f at a point c on the x-axis, is a local maximum if f of c is greater or equal f of x for all x near c. Similarly, we say that f of c is a local minimum value of f if f of c is less than or equal f of x for all points x near c. Here, and wherever else we say near all x near c, by that we mean all x in an open interval around c, an open interval that contains c. And so we're talking about situations like this. In the example, we're looking at the graph of the typical graph of a cubic polynomial, a polynomial of degree 3, which has two local extreme values. There's one orange dot here, which has the property that it's the value, the function value here is larger than any function value nearby, but it's not the global maximum because this cubic polynomial has the property that f of x goes to infinity as x goes to infinity. So f of x grows arbitrarily large. Still, there's this point of interest, a point c on the x-axis where the value is bigger than any value nearby, and that's a local maximum. Similarly, the other orange dot here near 2 on the x-axis is a local minimum. It's small, its value, the function value there is smaller than any f of x nearby. In this example, we see how local and global extrema coexist. This is the graph of the function f of x defined as 3x to the 4 minus 16x cubed plus 18x squared, where x runs over the closed interval from -1 to +4. And again, I've indicated the extreme values through orange dots. Again, you see 3 local extrema, one at 0, one at 1, one at 3. The biggest ever function value over this closed interval seems to occur here on the left at -1, and that would be a global maximum. So here's a list of interesting points which are marked in this graph. F of -1 equal to 5, that's the orange dot here, is a local maximum. It's larger than any value nearby, but it's clearly not global. As you can see, there are bigger values of f in this graph. For example, at -1, the value of f is 37, as you can calculate by substituting -1 for x in the formula. And that indeed is the global maximum of the function. It's worth noting that this is not a local maximum, because there is no open interval around -1 where the graph is defined. F of 0 equal to 0 is a local minimum. This should be clearly this is a minimum. This is smaller than every value nearby, and same for the value at 3, which turns out to be -37. Never. Okay, I have to check this, but it's small. It's very small. F at 3 is very small, and it's a local minimum because it's smaller than any value nearby, and at the same time it's the global minimum, not maximum as it says here. It's the minimum, obviously. It's a global minimum because it's the smallest function value you see over this entire interval. Finally, the other endpoint of the interval gives the function value 32 as the value at 4, and that's neither global nor a local extreme value, neither maximum nor minimum, neither global nor local. Finish this off with a little theorem which describes the circumstances under which extreme values exist. Under certain conditions one can guarantee the existence of extreme values, as in these 3 examples of functions defined over a closed interval, and in each of these examples you see a point C where the function takes a maximum value, and a point D where the function takes a minimum value. It may happen that one of these extreme values occurs at the end point of an interval, and of course it can also happen that the same maximum value occurs more than once over this interval. And so this is about existence of extreme values. It's called the extreme value theorem, and it says if your function f is continuous, that's one of the hypotheses, and defined on a closed interval from a to b, a closed interval on the x-axis, then f attains an absolute maximum f of c and an absolute minimum f of d at certain points c and d in the interval. And that's the theorem which describes exactly the situation we see in these 3 examples. Functions are obviously continuous, they're defined over a closed interval, and there are marked the points C and D where the maximum or the minimum value is attained. Down here are two further diagrams, graphs of functions which don't have this property. In the first example, the maximum value is not attained over the interval because the graph is broken, or in calculus language, this graph is not the graph of a continuous function. And here on the right hand side, the graph at the right endpoint of the interval from 0 to 2 seems to go off to infinity. Also, the graph indicates that the value at 0 is not included. So this is a graph of a function defined over an open interval, not over a closed interval. And that's the reason why here the absolute maximum nor the absolute minimum are attained. Next, we're going to look at critical points, which are a tool that allows us to precisely locate these extreme values.